Okay, we're doing our last problem for heat. And while these problems may look kind of complex, I always find them fairly easy to handle. So what we have here is, so it is again, this is some sort of a heating vat. It has mixing in it so that the material in here will be well mixed and the temperature will be uniform. So heat is obviously stored in here, so it has a characteristic temperature. This will be the low zone. This will be the hot zone, so theta L and some capacitance CL. And so heat is supplied here, and so heat will be stored here, but the idea is it leaks out into here. So this is the hot zone. So we have heat that we're adding in, but this zone will have a characteristic temperature, and since heat is stored there, we'll look at a capacitance. I'll call that CH. And we have two resistances. There's R1 with respect to the outside. So assuming we're not looking to heat the outdoors, R1 is probably pretty significant. Okay, so we want to retain the heat in this area. And I'm going to assume that this section here above the hot zone is perfectly insulated. So there's no heat coming out this way. So I'm not going to worry about that. So up here, we'll assume the resistance is perfect. And so we have higher resistance here going from the low zone into the ambient. And then there's a resistance that's intended to let heat from here come into there. All right, then we have our ambient temperature. So let's start modeling. We'll assume in both of these zones, we'll assume we have a constant temperature. And given with that, or I guess we should say uniform temperature all through here. The temperature here can change, so but we're just going to, better word would be uniform, not constant. It's kind of confusing a little bit. And again, in the next one, we'll change that to uniform. So that's saying we don't have any special hot spots or cool spots. So temperature here can change, but everything happens uniformly. Same down here. Okay, so we've got uniform temperature. So now, but heat is stored here, so we model that as a capacitance. So we have CH theta H dot equals heat in minus heat out. And I'm calling QH, here's QI, the heat that's being supplied, and QH is the heat that leaves out for here. All right. And then we have, again, assuming uniform temperature here, we have CL theta L dot equals the heat in, well, that'll be QH coming across, minus leakage to the ambient atmosphere, so minus QA. All right, so now we have to come up with QI. This is a heat source, so it is what it is. QH, so that's going to be, there's this characteristic resistance, 1 over R2, theta H minus theta L to drive the heat across. Likewise, we have R1, and we're going to have 1 over R1, theta L minus theta A. And once you're here, it's just a question of how much algebra you need to do. So we can convert to Laplace. So if we want to make a transfer function, this becomes, if we look at the low temperature side, that'll become CLS theta L of S. Okay, and just converting everything into Laplace, put the little s's on it. Okay, then we can go to this, substitute our stuff into here. That this one, CHS theta H of S, right here. And so now the algebra begins. Step 1, clear the denominator. That's what 1 to 1a. And I do the same thing here with 2 to 2a. And now if I look at this, what would I like to find? I'd like a transfer function that takes me between this supplied heat and the temperature in this vessel. All right, so that's my transfer function. Here's input, temperature here is output. Well, if that's the case, I don't care about theta H. So I can factor this out, bring the R2 CHS plus 1 to the other side, and now I have an expression for theta h. And you may go, so what? Because now I can go back into my other equation here. So let's see, which one do I want? Well, I can go into this equation. Here I can then replace, I have the theta L's. I like them, but I can go and insert my relationship I have here in for theta h. And now I can get an equation in theta L, theta A, and my input. So let's work on that. So here we have this. I'm going to solve for theta h. And if you look what I do here and bring all that over, R2CHS plus 1, here this R2QI plus theta L, all of this, I'm simply substituting all of this in for theta h. All right? So you want to see where all this comes from. Here's equation 1a. Here's theta h. So I solve for theta h, bring everything to the other side, and I'm substituting the result into this spot. And so that's why we have this R1 here, R1 multiplied over here. This was just R2 and theta L, but this R1 comes through, so that's from this, and the rest is theta h. All right, well, once we do that, now we have this input, the heat supplied, and we can view this as an input, the atmospheric, and so we can gather all the theta L terms. We'll take a bunch of this stuff to the other side. And so we have everything now in theta L, the temperature in the low temp region, our supplied heat, and the atmospheric. And so now we just divide everything through, and we can make this into two transfer functions, one relative to theta A as an input, and one relative to the supplied heat as an input. And that's the problem. All of which can be put into Simulink if you want to. And with that, we're done with our heat systems.